Are we streaming yet, Peony? Thank you. Thank you. Okay, so I will begin the lecture. We have a new topic today, but at the very end of last lecture, we were strapped for time, and I guess some of the recording got cut out. So I'm just going to very quickly, maybe in the first 10 minutes, cover the real essence of KMP. I mean, if you've processed Boyer-Moore, KMP in terms of its mechanics is really, really simple. So the idea is that if you have Zoom, okay, that's good. So if you have a text, think about, so we are doing KMP, Knuth, Morris, Pratt. So in some intermediate stage, we always reason from an algorithm from its in an intermediate iteration, some iteration, you've aligned J, so you're essentially trying to say, is there a match at position J in text with the pattern 1 to M? So the KMP is different from Boyer-Moore in that it will do a left to right scanning, so it's going to check is the character at position J in the text same as the first one? If the answer is yes, is the character at J plus 1 same as 2? So the scanning happens left to right. Now let's assume at some point, did I say I or I plus 1 as a mismatch in this slide? I'll just be consistent. So at position I in the pattern, you had the last match. That means that at I plus 1, there was some character x here and some character y here. Are you following what I've just said? And then there's a mismatch at that position. That didn't match. If that didn't match, then what do? What's the shift rule? KMP is saying, how do we shift? It says, find the length of the longest proper suffix of 1 to I. So it appears as if it's similar to, these statements all appear similar to what we have done with Boyer-Moore, but listen to the nuance of it. The nuance is that find the length of the longest proper suffix of 1 to I. What is 1 to I? It's the part where you saw matches. All these things matched. Okay? So what's the length of the longest proper suffix of 1 to I? When I say proper, it doesn't obviously include 1 to I. It will include 2 to I, 3 to I, 4 to I. In the worst case, it's I to I. Yeah? There are those many possibilities. Now, what's the length of the longest proper suffix of 1 to I that matches the prefix of that same length? So it's the longest that you want, the length of the longest that you want. In the traditional KMP, they didn't put any further constraint, but because we are doing a modern treatment of this problem and we know how Z algorithm works, you can add an additional constraint saying that the characters that come after this matches. So I'm going to highlight that in purple. So that character here is some question mark. That question mark is not equal to Y. Can somebody tell me why do I impose that constraint? It should not equal to Y. It's okay. Why do I say what will happen if I put that's equal to Y? Anybody? Yes, ma'am.
If it is equal to Y, then no, it doesn't have X at all.
Correct. If it is equal to Y, I go and shift it. So let's assume that I go ahead and shift it, assuming this is, let's pretend that this is a Y. So the shift would be somewhere like that. The pattern in the next shift would be, so this bit is same as this bit. Now that bit moves, the prefix part moves under where it was. but then you again have a question mark. If that question mark is y, then that position is x, you know, x triggered a mismatch with a y, you already know, so this would be fated to be a mismatch when you shift. So you're saying that I don't want to shift it such that it's the same character in the pattern, it has to be some other character, potentially it will avoid the mismatch. Now it doesn't, I mean, in a way you could pre-process it a bit more strictly, right? So all these things can be done a bit more strictly if you have a much more space, if you use a lot more space to store more information. So what's the more strict thing that you could do? Instead of saying this could be any character not equal to y, you can actually say what's the character. It should be these, what would be a length of the longest proper suffix that matches the prefix such that this character is an x. Now, reason we don't do it in the first treatment of this problem is because think about what x is. X is a character in the text. You don't know what the text is, and the pre-processing is always on the pattern, which means that if I have to do something agnostic to the text, then I potentially have to find the degree of freedom is what is the length of the prefix and what are all the possible characters that could come after that prefix. So essentially you have this, this dimension of your array, which would be order m times the alphabet size. So you could essentially you will have more space to process it. Now, if you understood this, then you shift it. So shifting is simple, right? So we call this thing SP of I. In fact, we talked the very end of last lecture, I told you what SP of I is, the length of the longest proper suffix that matches the prefix. And if the mismatch is at position I, so you have to shift by those many positions to get to the next point. So if you're going to be, if you shift it by I minus SPI positions, you're essentially aligning the prefix part under where the suffix previously was, and then you could start. The optimization is you don't have to do the left to right scanning from the front because you know that this matches with that region. That's exactly the same. That means that you could start straight away from that position. That's the optimization that you would get. Okay? Now, what would the only then, so that's the shift rule. There's only one shift rule in KMP, nice and clear. So what happens when you have all if there is an occurrence of pattern in the text, if I goes all the way to m, which means that the whole pattern is matched the region in the text, right? So if the whole thing matches, you just have to shift by m minus sp of m because you still have the longest proper suffix of 1 to m that matches the prefix. But then what happens to the next character after m? The definition of next character after m doesn't exist. You can say that any character that comes after the proper suffix length is going to be a mismatch, right? So you can bend your data structure interpretation to say that because there's no character, you can think of some dummy character, which is a unique one, and then it has to be a character that is different, okay? So that's all there is to KMP. So KMP is a very simple thing. I've already talked to you about what SP of I is. In fact, I'll just go back for recollection, but I'm not going to go through it again. So we saw this example and said, we reasoned y is SP of 9, 3, and y is SP of 1, 8. Sorry, I'll say that again. Y is the length of the longest proper suffix that matches the prefix at position 9 of that example is 3. Why is that 3? Why is it 1 at position 8 is something that we reasoned in the last lecture. Okay, with that statement, we wind up last week's topic and come into the brave new world of really powerful data structures. So what I want to flag before we start, housekeeping maybe, I should have started at the front. So assignment 1 has been released. So if you look at the assignment 1, it's based on the first 2 weeks of content. So 2 problems. First problem, you have to address it using Z algorithm. Second problem, you have to sort of come up with there's a problem spec, and you'll have to think about how you're going to vary Boyer-Moore to be able to address it. It's due end of week 5, the Sunday of end of week 5, so that's 2nd of April from memory of what I uploaded yesterday. Take a look. I'm going to have my consultation start. So I regularly will have 2 consultations each week, but from time to time, closer to the deadline, I end up opening up more consultations because it's basically demand driven. So check the consultation timings, go through your spec, and if there's something that is not clear, this should be the week that you should be coming and clarify that. Don't wait until week 4, don't wait until week 5. So one thing you will definitely find in this unit is you'll have a lot of help, support given to you. But then this is not the kind of a unit where you try and slog out an assignment in the last 24 hours of your deadline. Okay, it's an assignment that will. It's a kind. If you do the right things, it's a kind of a unit that makes you think, and the process of thinking is where you get most of the joy. Yeah, I can assure you that it is something where it'll give. It's very satisfactory. I mean, this is the reason why we all wanted to become computer scientists, right? There are many other units like this, but this is one of the reasons, right? Algorithms and data structures. I don't have to make it interesting. It is by nature interesting. Okay, with that, I just wanted to give you so what are we? We're transitioning from pattern matching algorithms that pre-processed the pattern and allowed you to search for all occurrences of a pattern in text in time proportional to the text length, right? So whenever Z algorithm and KMP and Boyer-Moore in week 1 and week 2 all pre-process the pattern. And in fact, if you think about the pattern matching using Z, it also can be treated as a pre-processing of the pattern because you have the pattern on the prefix side and you don't need the Z values beyond 1 to M if you're using Z algorithm for pattern matching. Okay? So Z algorithm based pattern matching, Boyer-Moore and KMP, and in fact, there are a few others of that kind, Rabin-Karp, rolling hash function. There are many other things that potentially you could pick up on your own, but the main things that we covered are pattern matching where the worst case runtime is linear in the size of the text. Now, in reality, what's going to happen is text is quite long. Okay? So if somebody from New York Times would want to say, I want to enable search for my users to search all the articles that were published in New York Times, the text is going to be a concatenation of a lot of things. They're huge. And patterns are often saying, did Knut appear in some, in New York Times? You'd be surprised that they've been, I think I sent you an article from New York Times. I suppose at some point I kind of remember making a post about this article that talked about Knut, right? So it would have to search this huge, humongous set of articles that they have published. The text is huge, so you can think of the text as concatenation of all possible articles that they have had, and you're searching for the word Knut. So that's going to be time proportional to the size of the text, okay? Do you see what I'm trying to say? Now, what would be a better strategy? It comes with a trade-off. The better strategy with that trade-off in mind, and we'll talk about the trade-off, is, well, when people publish articles, they are going to be static. They're there. You don't have to sort of keep running it over the text over and over again. So you want to pre-process the text into a data structure that allows you to have very fast retrieval so that the search is not proportional to the length of the text, but search is proportional to the length of the pattern. Pattern's always small, text is always there. Now, the trade-off is that you have to have space to store the text, right? So previously, in the algorithms like KMP and Boyer-Moore, all you needed was OM space. If you are not doing anything, it's basically the space proportional to the pattern size. In the algorithms that we're going to look in week 3 and week 4, you will see that it's pre-processing the text so that you will have to have that data structure stored. So it's going to be linear. The space will be linear in the size of the text. But the advantage is because you have that, the pattern matching. So often people want to search for various patterns with relatively static text. So you can essentially have one-time pre-processing once, sometime, and any pattern that people ask, you could do time proportional to the pattern length. Is that brief clear? Okay, so I must say that we're going to, for those who have come into this from 2004, I developed 2004 7 or 8 years ago, and there's some version of that you would have gone through. And I used to have BWT as a part of 2004. At some point, it got taken out because there are other considerations, rightfully. So I kind of adopted that material so that there's a nice block of 4 units where you're doing extremely powerful string algorithms and data structures that have real-world applications. So we're talking about BWT, Burrows-Wheeler's transform. Wheeler was the one who originally conceived this idea. Burrows was his postdoctoral student, and Wheeler managed to come up with this idea in 1970s, but said, everyone would know this idea, it's so obvious, and he put it away into his drawer, and Burrows made a fortune by going into his drawer and gee, these are gems of vignettes that need to be for the world to see, and that's how this came about. And then what they started, the reason why BWT was proposed was to compress files efficiently. Again, we'll talk about lossless compression in the coming weeks, so you will be seeing enormous links across the weeks that we do. Okay, a lot of subtle connections. So what is this compression? How many of you know what bzip program does? Have you ever seen bz2 as an extension for compression? If you're doing Linux machines, most of the Linux machines would have bzip2. So bzip2 is basically a Burrows-Wheeler's compression. So whatever file you give, it converts into a BWT, and there are a lot of compressive properties of BWT. So the first obvious practical application is Burrows-Wheeler's compression. In fact, it turns out that it gives you, for all reasonable text, it gives you better compression than lempel-ziv. We'll learn about what this lempel-ziv is. You will know what Burrows-Wheeler transform is shortly, but we will also learn in the lossless compression what lempel-ziv algorithm does for lossless data compression of text. You will understand why. So when you're using zip, the file, the archive that you do, that's essentially using a lempel-ziv algorithm. Yeah? So it's a lempel-ziv variation of what's called lempel-ziv 77, a paper that Lempel and Ziv wrote in 77. We're going to talk about that. But it turns out that if you compress Burrows-Wheeler's text, transform of a file or text, you end up getting better compression than gzip if you ran it with an optimization of speed and compressibility. Okay? So there are larger discussions about this point, but we'll postpone that to the lossless data compression week. Now, that's the first ostensible application. What is the second application? I'm going to show that Ferragina and Manzini, in turn of this new millennium, basically published this outstanding paper, these Italian computer scientists, which shows that you could use Burrows-Wheeler's transform to do pattern matching in time proportional to pattern length. So because the link that we are looking at is pattern length. Okay, so I will very quickly talk about this slide. You have all, do you remember suffix arrays from 2004? I'm going to ask you to revise that in preparation for this lecture, but I will not going to cover the algorithm to construct a suffix array. You've already learned it. Does somebody know the algorithm? What's the name of the algorithm that you've learned in 2004 to do suffix arrays? Long time, been there, done that. Prefix doubling. So it was Manber and Meyer who introduced this data structure, came up with this algorithm, and if my memory serves me correctly, that would run as n log squared n if you did it in a certain way. Okay? So n is the size of the string, log squared n. Log is often a manageable factor, so n log squared n is not a big deal. If you had something like an n squared, that you're in trouble, right? So and in fact, if you did the naive method of constructing a suffix array, it would be n squared log n, and we're talking about n being a million, n squared suddenly becomes intractable on your computers, okay? But if you had n log squared n, that's sort of reasonable, okay? So it's like, to give you a context, for a million, log n to the base 2 would be 20. So million times 400 is much better than million squared times 20. So that's the difference. Now, I would also say that end of next week, we're going to come up with another data structure related called suffix trees, which will allow you to construct suffix trees in linear time. If you construct suffix trees in linear time, you can construct suffix arrays in linear time. Okay? One last time, so you look out for it. Whatever we are discussing in the next 2 weeks will have a relationship. Finally, independent of the suffix tree algorithm, this is not examinable or anything for all the advanced students who want to think about it. There's a beautiful algorithm by Karkainen in 2005, 2006. I was in grad school at that time when we were excited when this algorithm came out. It guarantees a completely different approach to do a linear time construction of suffix arrays, and that's called a difference cover modulo 3 algorithm, DC3 algorithm in the circle, in the in-group. So if anybody wants to learn ahead beyond what we are talking about, because time is a very finite entity in this unit, Karkainen, another Finnish scientist, computer scientist, who basically came up with this beautiful algorithm, originally in a conference called AlanX, and then it got formalized into a journal, I think Journal of the ACM, if I'm not mistaken. If somebody needs a reference, just reach out to me. Okay, with that thing, we're going to talk about Burrows-Wheeler's transform. Now, think about the text Google, okay? In all the algorithms, you would have seen, string algorithms, you would have treated some special terminal character called $. So Google $, so $, is meant to be a unique character that is not in your alphabet. I mean, there's nothing special about $. It could be any unique character that is not in your alphabet. Whatever alphabet you're considering, you just need one extra character that is unique, okay? We're going to use $, as that character here, but in practice it could be anything, yeah? Clear? Now, Google with that $, the key point about the $, in the next 2 weeks, is that it is alphabetically or lexicographically smallest of all the letters. You should treat that special character to have a value that is the smallest of all other letters in your alphabet. Is that clear, everyone? Now, if you took Google $, or it's Google, which is actually the original word. So what's Google? It's 10 to the power of 100. Was it? That's the entity. So the quantity of 10 to the power of 100 is GOOGOL. Okay. Google got inspired by that name, for those who were looking for, or maybe there's a Russian writer called Google as well, I think. One of those two. I don't know the history of the company. Don't be evil company Google. We know that that's absolutely true. So GOOGOL is a word that a string we consider. If you consider all possible suffixes of that text, GOOGOL. So what are all possible suffixes? So GOOGOL is one suffix. The next suffix is OOGOL, OGOL, GOL, OL, L, and $, isn't it? They're all suffixes of the patterns. Now, if you actually sort those suffixes, they would be in some order. If you actually look at the figure on the right side here, so these are sorting the suffixes dollar, GOL dollar, GOL dollar, and so on. All these suffixes are sorted. There's a sorted order. Can you ascertain that they are in a sorted order? Okay. I grayed out some letters. Okay, I grayed out some letters because suffixes end necessarily at the end. But if you didn't treat this as a suffix, if you treat it as a cyclical permutation, a cyclic permutation of the string, meaning that when you go off to the right side, you come to the left of the string. So if you go to beyond m, you come to 1. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say m equals 10. And then when you go to the next right of 10, you come back to 1. So it's a cyclic string. Yeah? So can you see that what's in gray is basically a cyclic permutation of these reference texts. Can everyone be sure about what I'm saying there? Every line there is a cyclic permutation where the prefix part of that cyclic permutation ending at a dollar is your suffix, the regular suffix of the string. Now, what is a Burrows-Wheeler's transform? Okay, two things. What is a suffix array? It is essentially a data structure that records the sorted set of suffixes. So dollar is less than GOL dollar, is less than GOL dollar, is less than L dollar, is less than OGOL dollar. The fact that dollar is unique implies that you always will have a strict ordering. There won't be any partial ordering. In math, there are two different ideas, total ordering and partial ordering. So it will be total, it will be a strict order. You don't ever get ambiguities because dollar will disambiguate. At some point, dollar will tell, I am smallest. If everything else is the same, the dollar will, the first time you see the dollar, that will say, well, we are different. Okay? So it will create this thing, and suffix array is basically a data structure that records the sorted set of suffixes. Now, can you see that instead of storing them as strings, I can store them as numbers, right? So suffix array is an array of numbers. And what are these numbers? The positions where the suffixes start. Can you see that 7, 4, 1, 6, 3, 5, 2? If you go and look into the reference text, it will tell you where those suffixes start. So 7 implies that it's starting at position 7. 4 implies that it starts at position 4. Okay? Everyone clear? Now, if you have, now although we talk, whenever we talk about suffix array, we talk about this array of numbers. Mentally, you can think of this matrix of cyclic permutations in some sorted order, right? So that's what you're seeing out there. If you look at the very last column of that cyclic permutation matrix, do you see some letters there highlighted in red? Okay, so they always correspond. So if you sort these rows, I'm moving my mouse on the slide. So if you sort these rows, assuming that you also had these letters, the last letters out here, it's much more clearer on this side, the last letters out here corresponds to what's called a Burrows-Wheeler's transform of that original text. Now, what does that mean? Okay, in terms of proximity, this last column is cyclically before the first column. If you go this side, you come back to the front, isn't it? So this last column is one column before the first column in a cyclic sense, in a circular sense. Everyone clear? Anybody doesn't understand that statement? Okay? So I've told you what suffix array is. I've told you what's the relationship of the suffix array with the last column. Okay, if you found a suffix array 7, would you know what the corresponding letter would be in the last column? So 7 is dollar. So L is 6, isn't it? So here suffix array 4, so 4 is GOL dollar. So what comes in the last column? The one letter before, O. This is 1, What comes before 1? It's not 0. In the cyclic sense, it is 7, right? So it has to be $. Okay, it's circular. Okay, you can go in any direction of the circle. Okay, 6 is L. What comes before L is O. So that will be O out here. Similarly, 3 is that position. What comes before 3 is 2. So that would be that O. 5 is O again. What comes before 5 is G. So that would be, and so on. Have I convinced you that if I gave you a suffix array, you can trivially compute the Burrows-Wheeler's column? Okay. So if you construct, the whole idea of constructing a Burrows-Wheeler is take a string, compute its suffix array, whatever algorithm you want to use, and then use that thing to compute the last character. And if whatever the complexity of your construction of suffix array, it's only a one single pass on it. I mean, it's constant time to calculate the Burrows-Wheeler's corresponding letter in the Burrows-Wheeler's column. Is that clear? All right. So with that statement, we are going to talk about 3 obvious properties. None of these properties should confuse you. Now, I'm showing you a cyclic permutation matrix M. So throughout this thing, we'll be talking about cyclic permutations M. But in reality, when we are doing later on the algorithm, we don't ever have to worry about this matrix. Okay, we'll be much more space efficient. But for visually, if you look at the cyclic permutation matrix, whatever we saw in the previous slide, look at any column in that matrix. Do you agree that the letters in that column is some reordering of the letters in the original text? Any column will contain Google in some $, in some order. They have to be, because they've just shifted them, and they're all possible shifts. So each letter would be at every column in one of the shifts. So essentially what you would have is every column would be a permutation of the original thing. Yeah? Can you see that? Can you see that third column has GOO, GOL $ in some order? Similarly fourth, similarly first, similarly last, no matter what. Easy? Easy observation? Okay, now this gets interesting. Now let's take 2 successive columns, one after another, 2 things that come one after another. Now, if you extend this thinking, you will realize that if you take those 2, what's called a 2 mers, I'll write this, or 2 grams, which however, so in math, you have a string of a certain size, that's called 2 MERS or 2 grams. Okay, in general it's called k-mers or grams, yeah? So if you take 2 mers, what are all possible 2 mers in Google? So GO is a 2-letter substring, so GO is a 2-letter substring, OO, OG, GO, OL, $. And then there's $G. Okay, if you go cyclically, you can go cyclically in this string. So $G is like you go to the end, you have to come back to the front. Okay, can you see that every 2 gram is also there in any 2 successive? It's not just special about third and fourth. You take any 2 columns that are right next to each other in a cyclic sense, then you will find the 2 grams in them. Is that clear? Now, in fact, I just want to point out that this is true if you took the last column. What's the column after the last one? The first one. So if you go last, you go all the way to the first. So 2 gram is, if you took that column and that column one after another in that order, you would see 2 grams as well. Okay, that's an important one. In fact, this generalizes, if you take any k successive columns, you would start seeing all possible permutations. You would see all occurrences of k mers, k grams of that original string in some order. Okay, all good. Now let's start with Okay, we already said that. We already said this property too is that last column precedes the first column, comes before the first column in a cyclic sense. Okay, if you're going around from left to right, once you disappear on the right, you come back to the left again. Okay. So last precedes front. So L follows F. LF is the order that you have to keep in mind because we are going to talk about what's called an LF mapping when we are doing this algorithm. Okay, so we already said that the last column is where the idea is, the Burrows-Wheeler's transform of a string is. So when you talk about Burrows-Wheeler's transform of Google, you're talking about the string $OOGG. Okay. How do I? So what are the key points here? The key points here is that it seems at face value. I hope you appreciate one thing about it is that when you have a string, so think about a variable x in mathematics. You have a function on the variable f of x. So y equals f of x is taking the value x and changing it into y, right? Now, when you do f inverse of y, you get back x, isn't it? So it's invertible function. Now you think about these functions on strings now. Take the input string, something, okay? Then let's call it s now. You transform that string into a Burrows-Wheeler's transform. It's applying like a function that applies it, transforms it. And then what we have remarkably is the fact that you could invert that string to get back the original one without even needing the original string. You can throw away the original string, you could invert it. Okay, that's the reason why zip works. Essentially what it's taking is your file, converting into its Burrows-Wheeler's transform, compressing it. Once you invert is decompress and revert it back to the original. Okay, that's basically, it's magic if you have a function like that on strings. Okay, and if you can do it efficiently, even more so. Okay. Now, let's start with an easy method. When I say dumb is not meant to be a pejorative here, but sort of the basic level, maybe the most naive is the better word, a naive method of doing constructing Burrows-Wheeler's transform, inverting. So we are talking about not constructing, but inverting a Burrows-Wheeler's transform. We already know how to construct it. You apply your suffix array algorithm, and then from suffix array, you can compute the Burrows-Wheeler's transform. We already said the forward process has, you've learned an algorithm to do that. You just have to use the algorithm to construct a suffix array. Okay, are we clear? Now we're talking about inverting it. So you've given the Burrows-Wheeler's transform, how do you invert it? Okay, so what you have is $OOGG, the one in red. Okay, I'm keeping the string vertical so that we can map onto the cyclic permutation matrix as an insight. If you sort those letters, do you agree that that's what you would get? If you sort that string, Burrows-Wheeler's transform string, you would essentially get that. Now, those set of letters. Do you agree that that set of letters has to be the first column of your cyclic permutation matrix? It has to be. Why? Why does it have to be? Property 1, we saw that every column is a permutation, some permutation of the original thing, and the definition of a sorted set of suffix arrays, sorted set of suffixes, suffix array is nothing but a sorted set of suffixes, is that the first column has to be sorted, right? So if you sort those letters, you would end up getting the first column, okay? Now, what precedes the first column? The last column. Yeah? Cyclic sense, what precedes, what comes last comes before first, isn't it? So LF, remember? So if what precedes the first column is the last column, which means that I can now take what I've just sorted and put in front of it the last column. Do I have the last column? That's what the Burrows-Wheeler, last column is always the Burrows-Wheeler's transform. So you have this Burrows-Wheeler's transform column added to what the column that I've generated by sorting it, and then sort it again. And if I know that it's good, this any successive columns contains the 2 mers of the original string. So if I sorted it, I have recovered the first 2 columns of the matrix. Can you see that this thing is same as the first 2 columns? Now what comes before the first 2 columns? Same logic. Last precedes first, precedes second. So all I then do, I repeat, rinse and repeat. I have those first 2 columns that I've just generated, prepend the Burrows-Wheeler's column before it, sort. What does last, first, second contain? They contain all 3 grams. If I sort it, I'm going to get all the first 3 columns of my cyclic permutation. If I kept doing it, I would get it. Yes, ma'am.
I just had a question. Well, when you're sorting it after you have like more than 1 column, like on the last side of the slide, what are you like sorting?
You're sorting a set of strings of length 2, 1, 2, 3, 4. So I would have asked this logical question: what's the complexity of doing that? Maybe it's a good time. So what am I sorting? I'll just go back a bit. Oh no, actually we'll do it in this slide. So I have these 2. Okay, let's assume that you're in some intermediate stage and you added this thing. So what are we sorting? $G is 1 word. OGO is 1 word. $GO is 1 word, and so on. I'm sorting these words. If I sorted these words, because dollar is lexicographically smaller than any other thing, so the word starting with dollar will surface up. There's no other dollar. Then the words starting with G's come up, but GOL is lexicographically smaller than GOO. Does that make sense now? I'm sorting strings now. Okay? Is that clear? And if I did this, I can keep doing this. So now I have 3. If I put the Burrows-Wheeler's column before it, sort it, keep doing it, I get first, second, third, fourth, fifth. I'm recovering 1 gram, 2 gram, 3 gram, 4 grams, all the way to whatever, if the size of the string is n grams. Okay? The result of this kind of method, this naive method, is that I'm going to recover the entire cyclic permutation matrix, not just the string. Okay? I'm going to, if the string is of length n, including the dollar, I'm going to get n squared letters appear, right? Now, what is the original string? Look at the first row of your cyclic permutation. It will be dollar followed by the string. The original string is Google. That will be the first row of that, whatever I've recovered. Okay? You see that? Instead of dollar being at the end, it's at the start, but we kind of can easily look at the first row and put the dollar at the very end anyway. Okay? So what's the complexity of doing, so we have already said that. What's the complexity of doing this method? Okay, maybe it's figure out, think about it, maybe you will not answer it now, think about it during your self-study. If you did, I've already said it's a naive method. I want you to think about what algorithm would you use if you want to sort something with fixed width? How do you sort, what is the go-to algorithm for you if you were sorting words of a fixed number of letters? Okay, radix is a very good option. Okay. Okay, so in fact, radix sort allows you to do, if you have n words of W letters, you can do it in big O n times W, which is W is the width of the thing. because W is, if it's small and a constant, you can say it's a linear time algorithm, except that no sorting algorithm theoretically is faster than n log n. W, as the string grows, approaches log n. Okay, so there's no free lunch in algorithms, so algorithms have to be, there's no linear time sorting algorithm unless you made some assumptions. The general purpose algorithm would be n log n. Okay, but with that in mind, figure out what's the complexity of doing the naive approach. Are you all with me so far? Yes. Okay, let me just look at the question online. So, how do you even get the third column, which you then sort lexicographically? Well, you get the third column by taking the first. So, you're right now on the screen, you have, I'm assuming, which slide is it? 15. So, I'll just go back and so that the stream looks at slide 15 before I answer that question. So how do you get the third column in that context? So the one who has asked the question online. So right now I'm assuming you know how you got the first two. That's basically sorting from the previous one. So to get the third column, you just to these two columns prepend the red column before it. So can you see my mouse? If you put that red column before it, you would end up getting this state here that I'm hovering my mouse over. So that was the previous two, and then the one before is the Burrows-Wheeler's transform. You always start with the Burrows-Wheeler's transform. You have it already. So all you have to do is take whatever you've sorted, whatever you had as a result from the previous iteration, and to that set of, in this case, 2 grams, you prepend the Burrows-Wheeler's column symbols. Now you have 3. You have a string. You have a column with 3 letters in each row, isn't it? You have set of 3 columns, and each row you have you essentially have n rows and 3 columns because you have taken the first 2 that you had sorted previously, and then you added the Burrows-Wheeler's column as your first column to those 2. Now you have, and then you sort it, you get 3 columns. Does that answer the question at all? Well, if it doesn't, then you can ask a question later on and I'll come back to it. Okay, so can we do better than that naive approach? The answer is yes, and Burrows and Wheeler came up with this idea of doing it efficiently. And for that, you need to understand, remember that all you have is the last column. So everything else that you're seeing on the screen is just for your mental reference. Keep remembering that all you have in this algorithm is the last column. Okay? So how do you recover the original text from the last column, the Burrows-Wheeler's transform column? The idea is that you would want to recover it by mapping letters in the last column to letters in the first column, because first column is the most deterministic column. Why is the first column most deterministic? Because I know the order in which the letters will fall, because they have to be the sorted order of letters in the original. Whatever the string, the first column is fully sorted. Okay? Whatever the string, the letters in that string, if you sort them, you get the first column. So you kind of know by default what so it has a lot of structure in it, a lot of sort of patterns in it, okay? But I know that last column precedes the first column, so all I'm trying to do is find my way by mapping a letter in the last column to a letter in the first column. Once I get the letter in the first column, I know its preceding one is in the last of that row, so I can go from last of one column to the first, wherever that letter appears in the first. Its preceding letter would be the last in that row. And then now I have got to the last again. So L to F, F to L. Then I have to say, where does that come in the first column? That L has to be mapped to the first. And I repeat the process of mapping last to the front. And let's see what this means. Now, if I didn't know anything and all I knew was dollar was my special symbol, do I know that my first row will have to start with a dollar for any string? The first row has to start with a dollar, right? Now, do I know what the last letter, so if you look at the Burrows-Wheeler, so you have the Burrows-Wheeler's transform. If you have the Burrows-Wheeler's transform, preceding the dollar would be the first letter in the last column, right? What comes before dollar? It is whatever is the first letter in your Burrows-Wheeler's transform, the last column. The first letter in the last column will be a character that precedes dollar, because L precedes F. F, if it's dollar, L would be whatever the character in the last column. So dollar so essentially, if you know dollar, if you look at the very first row, it has to be a dollar and its preceding letter would be L. And that L has to be the last letter of your original string if you didn't consider the dollar. Dollar is only a special terminal, right? The last letter has to be L. So essentially what you're trying to do is recover this algorithm. We'll talk about how you actually drive this algorithm, but logically you want to recover the algorithm last letter. I mean, when I say last letter, dollar is the last letter, but the real last letter beyond that special terminal one, you first recover that last letter of the original string without the dollar, and then the second last, then third, fourth, fifth, all the way to the first. You're recovering backwards, okay? The recovery is backwards. So if I magically knew where does this L fall, so we'll start with, so here's the start of your thinking. Start with the last letter of your first row. What is the last letter of your first row? It has to be the first letter of your Burrows-Wheeler's transform. So you start with the first letter of your Burrows-Wheeler's transform, L. Now you say, if you magically knew somehow, mathematically, if you could compute where does that letter, that specific letter, not any letter that looks like it, that specific L, where does it fall in my first row? If I assume that I had a first row, if I had a cyclic permutation matrix, you don't have to compute a cyclic permutation matrix, but if you think about where does that first letter of my Burrows-Wheeler's transform appear in my first row of my cyclic permutation matrix, then I can map from that point. Visually, we can say very clearly know that there's only one L in this entire string, Google. This L appears here, okay? This is not a given. We have to figure out how do you map it, right? We don't know what position. The position here, going from position 1 of L to position 1, 2, 3, 4. Position 4 of, it's a shame that I can't write on this. Anyway, I can't seem to, oh, is it this one? Okay, fair enough. That's fine. So position 4, that's position 4. So I'm pointing my mouse to it. For those who are online, everyone can see where my mouse is, right? So this maps to position 4. What comes before L? It is whatever is in the last column of that row. So what comes before L is the last letter O. Now I'm saying, where does this O fall? Well, if I found a way that this O, by the way, this is O, there are many different O's, right? There's a first O there, the second O there, third O there. But this is basically the second O that we are looking at, right? Oh, sorry, is it first or? Okay, it's the second O that we were looking at. Yeah. So this second O happens to be at position position 6 in the first row. I need to know how do I map from any given letter in the last column to some position in the first column, because if I get the position, so for instance, I got from L, go to the first, so if I knew how to find this position, I know the previous letter, I can recover one letter previous to that, that is O. So I now have LO recovered. Now if I know this O appears here, I can recover one more letter G. So GOL has been recovered. If I know that this G maps here, then its last letter is O, then OGOL has been recovered. And if this O maps out to position here, I can recover one more letter at the last, which is OOGOL. Can you see what I'm trying to get at? The recovery is essentially a function of starting from the first letter of the Burrows-Willis transform, go to some position in the first, so that you know that the last letter in that specific position has to be, all you have is the last row. Okay? You don't have the first row. You essentially can use this mapping, L to F mapping, to recover one extra letter in each iteration. Is the plan at least clear? We'll see what this means and how we drive this in a bit. Okay? Is the plan clear? All right. So if that's clear, this is $1 million observation. We're going to see this observation as an example in the next slide. I'm going to go slow. Don't worry. If it appears a bit complicated, it is not. So all you have is your last column here. Now, the problem is that in the previous slide we saw O's. There are first O, second O, third O. So essentially, if you have any character that appears in the last one, appears one or more times, isn't it? It can appear one time or two times or three times, or depending on the original string. Whatever the number of letters, number of times you see any character, that many times the letter would appear in some order, because that's we said every column is a permutation of the original string, right? So let's assume that there's a character called phi that appears any number of times, let's say some 3 times in this example, okay? The observation is saying that if you have a sorted column, first column is always sorted, right? If you have a sorted column, those letters will have to be in a block in the first column. Can you see that? Okay, I'll go back and forth between 2 slides now. So this is your last column. O appeared at position 2 in the last, position 4 and position 5. Okay, it can happen in any permutation, but in this example it was 2, 4 and 5. In the first row, in the first column of that cyclic permutation matrix, the first column of the cyclic permutation matrix, can you see that these O's have to fall together? That's the definition of being sorted, isn't it? All O's have to be grouped together. You cannot have O and A and then something else. It's not sorted. Okay? So go back again. Now, corresponding to this, each of the occurrence of phi in the Burrows-Willis column, potentially, you don't need them, you don't need those specific characters. Potentially, there's some character that comes after phi. Some character that comes after phi, after the letter phi, not 5, it is the Greek letter phi. Okay, this letter, this fancy piece here. What comes after that? Because last precedes first, there will be some character in the first column of the cyclic permutation, isn't it? And that could be any character, really, this and that. So can you tell me what is the order in which if I have to sort them, do you agree that this has to be less than or equal to this, has to be less than or equal to that? Those letters have to be lexicographically ordered because it's a sorted column, definition of sorting. Now, if that is true, if the phi appears in the first column and phi is before the first, last comes before first, the combination of letters that are in the last and first is a 2 gram, isn't it? Is a a string of, a substring of length 2. So there will be some suffix where the phi will be the first one and the character after that is whatever you saw as the letters against phi. Letters against phi is f of I1, f of I2, f of I3. You will see phi followed by f of I1, phi followed by f of I2, phi followed by f of I3. You will never get it in any other order. Why? It's because it is a sorted set of suffixes. If, let's say that these were equal, let's pretend that this was psi, phi and psi. So let's say, let's make it easy. Let's call this f and let's call this s. So if this was an f, these two were f's and these two were s's. So you would have fs appear in those two columns. Now, why would it not swap the order? Is because the fact that this came before this implies that there were some letters after the first column that made the order of one come before the other. So essentially the order is preserved when you have a bunch of letters here. They will have to fall in the same order as of the first letters, the corresponding letters in the first column will have to be in the same order. Okay, does that make sense? And in fact, this should make it very, very clear. O is preceded by O precedes G. This O precedes L. This O precedes O in a cyclic sense. All clear? So if you see O appears here, GLO appears in the second one. Okay? They don't have to be distinct. They can actually be the same letters. You would still have that same order. Okay? All right. So, okay. One more thing. So, where does this phi's, so this is the letter that we were tracking. So this letter phi appears one or more times. In this case, it appears 3 times. There's a block of phi's that appear in the first column. I think we are all sleeping now, but morning time is not the best time to think about algorithms. But this is important because this will set the agenda for what is how you do the construction. So please pay attention for your own sake. So do I know easily what is the block in the first column where phi appears, can I easily track it mathematically? Now, it turns out that this phi will be a function of the rank of that symbol in the set of letters in the original text. What do I mean by that? Okay, let's for that look at an example. Look at the first column here. What are the letters you see? $, G, L, and O. There are one or more of each of them, right? You see a $, unique. You see a G, you see an L, you see an O. Do you automatically know what order they appear? Obviously, $, is less than G, is less than L, is less than O. Yeah? Now, what is the rank of $? Which position does $, appear in? Position 1, right? I mean, so let's figure out how to calculate it later on, but just looking at the slide, what position does $, appear? It appears in position 1. The rank of $, is 1. What's the rank of G? Where does G start? At position 2. So rank of G is 2. where does L start? It starts at 4, isn't it? And where does O start? It starts at 5. So all I need to do is if I have the Burrows-Wheeler's column, can I compute the rank of the unique letters? It's a very good question. Think about it. All those who are trying to feel a bit sleepy, will wake you up. Can I find the rank of letters from the Burrows-Wheeler's column? Because that's what we have. And if somebody tell me why and how. Can you find the rank? Do you know how many letters you have? So if you knew the alphabet of your, let's say that you had an alphabet. Every time you see a unique letter, you know how many times the letter, you can actually go in one single pass and count how many times each unique letter happens. Okay, if you pass from the first, so you go to the last column, keep parsing it. Did I see L before? No. Well, L is a new letter. It has appeared one time. Did I see O before? No. Well, O is a new letter. It appears one time. Is dollar, did I see dollar before? No. Dollar is a new letter. I've seen one time. I see an O. Well, I actually seen an O already before, so now I've seen O twice. I've seen this thrice. O now thrice once I come here. G I haven't seen before. I've seen once, and the last one when I parse it, I've seen G before. It's twice. So what do I have? I've seen L one time. I've seen O 3 times, a dollar one time, and G 2 times. If I sort the order of these unique letters, I get a sorted order of these things, and from the number of counts, I can compute the rank. Okay, it's a very simple, and if alphabet size is a constant, so in one single pass, you can essentially maintain an alphabet-sized array, sort it, which is a constant, and then you compute the rank. Where does each column, each character appear? You understand what I said there? Do you understand what I just said there? Okay, maybe it requires writing then. Too early in the morning, huh? So if I parse that, I saw L one time, I saw O 3 times, I saw dollar one time, and I saw G 2 times. Are you happy with that statement? If I sorted it, I would get dollar one time, L one time, yeah. Oh, sorry, G one. Okay, G comes before L. G two times, then L one time, and O 3 times. Isn't that what we have here? So, what is the rank of dollar? Well, dollar is a unique letter is 1. Okay. What's the rank of G? It starts after 1, so it has to be 2. Okay. Okay. But then there are 2 of them, so 2 and 3 are taken by. So 2 and 3 are taken by G. So it's cumulative sum basically. So what is the rank of L? It has to be whatever the cumulative sum plus 1, 4. Okay. Okay. So it starts at 4. So whatever. So it's not. You don't have to do a cumulative sum. Whatever comes after. So 2, 3 is taken. It's 4. There's only one of L. So 4 and 5. So it's essentially the sum of these two, not those two. So this and that will give you that. So this and that will give you the rank of O. Okay. So what you have here is positions where in the first one, if you look at the first column now, the rank tells you dollar starts at 1, G starts at 2, L starts at 4, and O starts at 5. So that's what a rank is. So it's a very simple arithmetic that you would have to do to compute the rank. Now, so whenever you see a letter, you know immediately if that letter in the last column, where is the block of that letter. Rank of, if you look at the rank, it will tell you that in the first column it starts at position, some position, and if there are one or more letters, it will basically be those letters in a block. Now, but then, which order, so which letter is it? If for instance, if I'm looking at that O, it corresponds to the second O here, right? So this is the first O, second O, third O. In fact, it follows the same order, first and second and third. It's because I told you that the thing that sets the order is essentially the sorted orderedness of the suffix array, of the suffixes. And that starts with the first row, and if the first rows are the same, then the second, if the second rows are the same, the third, and so on. So essentially what the order in which any character appears in the last row will be the same order in which it would appear in the first row. Is that clear? So if I have to look at this O, I have to say which rank, what is the rank of O, which I already know how to compute. So it starts here, and is it the first row? I have to just say how many times did I see an O before that position. If I'm looking at that cell, that O, how many times did I see an O before that? 0 times, right? If I have not, that means that rank plus 0 would be that O. Rank of O plus 0. Now if I saw this O, so what is the rank of O? It's pointing to that position. How many times have I seen an O before that position? Once. So whatever the rank plus 1 would be that one. So if I look at this O, what is the rank of O? Is that position. So I know it falls there. Which O is it? It is how many times did I see an O before that? 2, right? So rank plus 1, 2. That's that O. So all you have to do is do the computation of rank of a letter and number of times I've seen that letter from the beginning of the Burroughs Wheeler to that position. Okay, we will see what that means as an example. Okay, I've given you the essence that to compute a mapping from last to first, the position is computed as rank of that character plus number of times I have seen that character from the start to the letter. So letter is you're pointing to the letter at some position I. So 1 to I exclusive. You only want to compute that how many times I've seen that letter before. So if you look at I is not included in your count. How many times have I seen? If it's the first letter at I, then I have not seen anything before. So the rank has, the position has to be the rank of that letter, plus 0. If I see the one time before, then it's going to be the second instance, right? The second instance I'm seeing, I've already seen one before, so it's going to be rank plus 1, okay? And blank plus 2, and so on. Now, let's look at an example, and this will hopefully make the mechanics very clear. So whenever you learn an algorithm complex first time, it looks what's going on. A few attempts it will give. Okay, so here's just an example here. I've already done this example. If I'm looking at I equals 4, so that's basically I equals 4. So L of 4 is letter O, correct? What is the rank of letter O? It is 5. We've already said, rank of letter O is 5. Okay? So I'm going to highlight that. So 5 is associated with the rank. Okay? So I can compute this rank table in one pass of the Burroughs-Wheeler's transform. I've convinced you that, right? So I know that if I want to find out where does this O appear in the first column, I have to find the rank. Rank is 5. How many times have I seen an O from 1 to I exclusive? I exclusive, meaning that from 1 to the one position before, inclusive. So you have to exclude that position. Number of times I've seen is once, so it's going 5 plus 1 is 6. So if you look at the 6th position, that is pointing to that O there. Does that make sense? Okay, so now let's start from the very beginning. So we'll just reconstruct the string so that we all are now accustomed to this crank turning. I've given you the intuition, now let's crank turn, yeah? So if I have a Burrows-Wheeler transform, I have convinced you I can compute the rank table in linear time, correct? I can compute this table just from these letters. And I've told what to do on the board, right? Now, then you start recovering from the very end. So you already know the last letter has to be $, and the first letter in the Burrows-Wheeler transform would be the last non-terminal letter. So when the $, is a special letter, the regular letter, last regular letter in the string. Okay? So L would be, the first letter is L, so L would be where you start the process. Okay? L of 1, last Burrows-Wheeler transform, the first letter is small l, that's where you start. Okay? Now, where does L appear in the first? So how do you reason this? Anybody? Somebody wants to tell me how you would reason this. Where does L appear? I have to know the rank of L and number of occurrences of that letter from 1 to I, where I is right now 1, right? We are counting from 1. From 1 to 1 exclusive. 1 to 1 exclusive is what? Nothing, right? There's nothing before. So what is rank of L? Look at the table. 1. What is the number of times I've seen an L before 1? No, there's nothing before 1. That means that 0. So 1 plus 0 is the position where, I'm sorry, I must say the rank was 4. 4 plus 0, I got carried away looking at students. I'll say that again. So rank of L was 4. If you look at the table, I was not looking at the table, I was looking at you guys. So rank of L is 4. Number of times I've seen an L from before 1, which is nothing, is 0. So 4 plus 0 is 4. The position that we are looking at right now is 4 for the LF mapping. Okay? This is for your this matrix here is for your reference of its correctness. In reality, you only have a number. You have the Burrows-Wheeler transform and a number, position. Now, do you know what comes before L? Well, it's easy. Look at the last column. Look at the Burrows-Wheeler's column at position 4. That is O. So, L recovers O. The one letter before L is O, isn't it? So, because this column comes after the last column. Last comes before first. We know what the mapping is. The one before is O. Okay? So, immediately I can recover an extra letter. I've started with L. I mapped it to 4. I look at the last letter for that position. Burrows-Wheeler's transform of that position, 4, which is O. So when I get that, I essentially have that letter recovered. So the LF mapping has been done. So we said the first character at position 4 is same as L. This is same as this is what it's saying. And this letter precedes this letter, which means that what I am allowed to do is to recover one letter before L, which is that letter in red, which is O. So I have now recovered, I know what $1 was, L is where I started, I recovered O. Now my position is O. Okay, now I'm looking at I equals 4. Okay, now what is the rank of O? Repeat, rinse and repeats. What's the rank of O? Now I look at this at the rank table so that I don't miss. So what is the rank of O? Is 5. How many times have I seen O from 1 and before the current I, which is 4? How many times have I seen I've never seen, no, I've seen once. I've seen once, see, this position 2. So I've seen, so the rank of O is 4. How many times have I seen an O from 1 all the way to before that position. So the current I is originally the I was here, I mapped to the first one and I recovered the last one. Now my I is here. Rank of O is 5. Number of times I've seen an O at or before is basically 1. I've only seen 1 O. So that is, we have to figure out how do we keep track of that. Okay? We'll have to keep, in fact, it's a good exercise for you to think. How do you keep track of how many times I've seen something? So rank of O is 5. 5 plus number of occurrences of O from 1 to that position is 1. So 5 plus 1 is 6, isn't it? So if it turns out that I can compute the next mapping of that position, that O, to 6. Okay? Beautiful, isn't it? I can see some of them have that twinkle in the eye. That's correct. This is an algorithm that is very satisfying when you get it. And it will only a matter of a few more attempts and you will see how beautiful this is. So, well, I got 6. What comes before 6? Well, whatever is in the last one, that is G. So I can then recover G. So now I have GOL dollar. Now I is pointing to that position 6 now. Rinse and repeat. What is the rank of G? Rank of G is 2. How many times have I seen this G from the first all the way to before that position? 0 times. So this one has to map to rank plus number of occurrences. 2 plus 0 is 2. That means that it will have to map to 2. What comes before G? It's whatever is in the last row of that position, which is O. So now I is pointing to 2. Okay? What is the rank of O? We already said rank of O was 5, right? How many times have I seen an O at or before, from 1 to that position exclusive? 0 times. So which means that it's going to be the position that this maps to would be 5 plus 0, which would be 5. What's the character before that? That is O. So I'm actually recovering one more O. Okay, now we'll just complete one thing and so show where it stops. Now that position is 5. What is the rank of 5? Rank of 5, what is the rank of O here? Again, it's 5. How many times have I seen an O at or from start to before this position? It's 2 times. So 5 plus 2 is 7. So my next position would be 7. That's there. Okay. The character that comes before that would be in the last column. So I've recovered G. Okay. Wherever it maps to, that last letter is what I've recovered. I've recovered G. And hang on, one last step. So what's the rank of G? Rank of G is basically 2. How many times have I seen a G from start to before that position? I've only seen it once. So 2 plus 1 is 3. So I would get the new position 3. What comes before that is dollar. Once I get the dollar, stop. Because I've recovered everything. Okay? This is magic, yeah? It's one of those algorithms which you wish that you were born a bit earlier and it could have been called whatever your surname, Wheeler's algorithm, right? So but I must say that many algorithms are beautiful in hindsight and it's always a tribute to the original makers, Wheeler in this case, to be able to see in foresight this beautiful structure. Okay? And have I convinced you this algorithm exists? The only thing that you have to figure out, you know how to compute the rank, you know how to do the mapping. The only thing to figure out is what would be the strategies, and I'll let you think and over the self-study time, what's the strategies in tracking efficiently or in some way the counts, because the counts, number of times any character appears from 1 to a thing can't be a linear search every time. Okay? So you want to figure out what is an auxiliary space that is acceptable, that allows you to not search from the start but search from some middle points or something like that, some intermediate points that you store, pre-process and store to allow you to do the computation efficiently. So we finished the the main part of the recovery. I'll very quickly go to the essence of how do you do exact pattern matching using this algorithm. It's very, very simple if you know this rule. I will just first talk about how do you do that. So we already said what the pattern matching is. So what is the pattern matching problem? You have 1 to m pattern. You want to find it in the text 1 to n. You want to find the number of times that pattern appears and where it appears, right? Now, instead of having, so what you're trying to, the algorithm is basically trying to say that I have 2 pointers, start point and end point. When you have to search for a pattern, you have to search for a pattern in the reverse order. Like you're recovering something, you are searching for the pattern in the reverse order of the pattern. So you have to search for the mth character of the pattern first, then m-1, m-2, m-3. Now each time you are doing it, you have a start point and end point pointing to the Burrows-Wheeler's column. So you have a Burrows-Wheeler's column as your index. So what are you doing? You're taking the text, converting it into a Burrows-Wheeler's transform. Okay? You apply your suffix array algorithm, convert it into a Burrows-Wheeler's transform. Now you have the Burrows-Wheeler's transform as your index. Okay? The index is of size of your original text. You can throw away the original text. You don't need the original text. All you need is a suffix array and the Burrows-Wheeler's transform. If you have a suffix array, you have this Burrows-Wheeler's transform anyway. Okay? So you start with a start point, end point. Initially, start point is pointing to 1, end point is pointing to the n of your, n is the size of your text. So first letter and the last letter is where it's pointing to in the Burrows-Wheeler's transform. So when you search for one letter at a time, reverse, so pattern, you're going from mth letter, m-1th letter, and so on. Every time you're searching for a letter, you are reducing the scope of start point, end point, so that that start point, end point is pointing to all suffixes that start with that letter. So every time you say, you search for a letter, you're essentially changing, you're updating your start point, end point. They always will be pointing to, they'll always be pointing to the, to a block of your suffix array where that pattern that you've searched. If you've only searched for the letter M, all positions in the suffix array where the letter at position M appears. If you have searched for the one before and the last letters, m-1 and m, all positions where m-1 and m letters appear in the suffix. And as you are recovering backwards, when you end the algorithm, you will essentially find out all positions, start point to end point in the suffix array where that whole pattern appears, because you've gone from m-1, m-2. Once you reach 1, you have searched for the whole pattern. Wherever the pointers are pointing to in the suffix array will be your pattern matching. How long does it take? It's time proportional to, if you, with some auxiliary space, it's time proportional to searching each letter, m, m-1, m-2. So that's the agenda. Now, initially you're putting m start point at 1, end point at n, and here's the thing. I want you to pay attention to what this is saying. Whatever letter you're searching, okay, whatever letter you're searching in an iteration. So initially the iteration starts at position last letter, then the second last letter, then the third last letter. That will be a single letter, right? A letter in your pattern. So if you, the start point is updated as rank of that letter plus number of occurrences of that letter from start, from 1 to the previous start point, exclusive. So you're not going to include, just, it's very similar to what we have done in the recovery. Rank plus number of occurrences. Here, the character is not coming from the last column, it's coming from your, essentially your pattern. So rank of the pattern plus number of occurrences of that letter from in the Burrows-Wheeler's from 1 to the previous start point, exclusive. And then where does it end? The same thing where you are saying that rank of the pattern plus number of occurrences of the rank of that letter in the pattern plus number of occurrences of that letter from the start to the end, inclusive minus 1. The reason why you have the inclusive exclusive business is you will see once you do the algorithm that it makes mathematical sense to have that structure to narrow down your search as you do it. We'll do an example very quickly. So pattern is GO. This text is Google. What time is it? Oh, plenty of time. Okay, I can slow down as much as possible, so no need to hurry. So GOOGOL dollar. Do you agree that the Burrows-Wheeler's transform we have already seen is LO dollar OOGG? I've just written it horizontally now rather than a column. I've written it horizontal as a row. Yeah. Yes? No? you gave me that 1,000-yard stare. I'll just go back. Can you see that LO dollar OOGG? That same thing I've written left to right. That's all. LO dollar OOGG. And suffix array index, we have already said what this index is, right? So we know that they are essentially, when you have the definition of a Burrows-Wheeler's transform comes from a suffix array. So one letter before 7 would be L. So that's 1, 2, 3, 4, 5, 6, 7. One letter before 7 would be L. So corresponding to 7, the letter before is L. Corresponding to 4, the letter before. So 1, 2, 3, 4, the letter before is O, and so on. So this and this are intimately connected. Okay, we have convinced you. Now let's search for this pattern GO. It's a very simple thing. 2 letters. We'll just see what happens. What did we say we should start the original start point and end points to? Point the start point to 1 and point the end point to N, right? So start point is pointing to the first letter of the Burrows-Wheeler, end point is pointing to the last letter before you start the algorithm. And how do you search? You have to search for the pattern in the reverse order. The pattern is GO, so you have to start the other way. So what's the first letter you have to start searching on? O, isn't it? Okay, you start on O. Okay, so we are starting on letter O. Okay, so we are starting on letter O, and this is the formulas that we have to use. Okay, and you will see why this works quite intuitively, because you already know why it works for the recovery. You will see why it will work for the pattern matching as well. So start point is 1, end point is 7. Okay, now I will go back because it's a cleaner slide. Start point is 1, end point is 7. The character that we have to look at is O. What is the rank of O? Do you know what the rank of O is? Yeah? It's 5, isn't it? Rank of O is 5. I mean, I've not put the rank table here, but you will see in the previous thing, we know that rank of O is 5. How many times have I seen, I'll just go to the front side. How many times have I seen O from 1 to wherever the start point is exclusive? So I'll go back. How many times, if start point is here, how many times have I seen an O from 1 to before that previous start point? None. So 5 plus 0 would be my new updated start point. Now look at where that points to. It points to the start of it. Okay? The first occurrence of O, basically. Now, what is the next rule? How do I update the endpoint? Rank of O plus number of occurrences of O from 1 all the way to the current endpoint, inclusive minus 1. So my current endpoint is this, rank of O. Remember, rank of O, because I'm searching backwards, is 5 plus number of times I've seen an O from 1, the first position, to the current endpoint, inclusive. How many times have I seen an O? 3 times. Minus 1 is 2. Okay, so 5 plus 2 is 7. So my new endpoints would be pointing to 5, and ending at 7. Look at the first letters in the range, the updated start point and end point. It points to O's, because that's the letter you searched. Now we have to do one letter previous to that. This is really magic, man. So I actually had a chat with, in one of the conferences to Ferragina, and I was fawning about how he came up with this idea, and he was saying that he was surprised that Burroughs and Wheeler did not take down this low-hanging fruit. But he called it low-hanging fruit because he might be modest, but I feel that it's only low-hanging in hindsight for us. They were able to see it in foresight. Foresight beats hindsight by a darn sight. So, okay, now the current start point, end point. I've recovered O. So what is the next letter to O in the reverse direction is G, right? So what is the rank of G? Rank of G is 2. How many times have I seen a G from 1 to the current start point exclusive? How many times have I seen a G from the first position to the current, so exclusive? 0, isn't it? Am I missing something? Is it 0? You said 1. Where did I see a G before? 1 to this position. The current start point. Current start point exclusive. That's what this slide says, right? 1 to start point exclusive. So G is, the rank of G is 2. A number of times I have seen a G from 1 to the current start point exclusive is 0. So it's 2 plus 0 would be my updated start point. So now my G is pointing out here. Now how do I update the endpoint? Rank of G is 2 again. Number of times I've seen a G from 1 to the current endpoint inclusive. Okay, so I can go back again. Can you see that it's an inclusive bracket here? That's an exclusive, inclusive, minus 1. So number of times rank of G is 2. Number of times I've seen a G from 1 to the current endpoint inclusive is basically 2. Minus 1 is 1. So 2 plus 2 minus 1 would be 3. Now if I update it, lo and behold, look at where the current start point and current end points are pointing to. Okay, 2 and 3. Look at the first 2 letters of that range, GO. Now let's actually do one more example. Let's actually have another O. OGO is what we are searching. Okay, technically there has to be only one occurrence of OGO, right? Let's do OGO. So what is the rank of O? Yeah? 5. Rank of O is 5. Number of times I have seen an O from 1 to the current start point exclusive? 0. Because I have not seen an O from 1 to the current start point exclusive without considering that position. That's what exclusive means. So 5 plus 0 is 5. My new start point is 5. Hold that in mind. What's my new end point? Rank of O is 5, right? Rank of O is 5. Number of times I have seen an O from 1 to the current endpoint inclusive, minus 1. So 5 plus 1, 6, minus 1 is 5. So endpoint is also pointing to 5. So which actually look at that position. So position 5, 2, 3, 4, 5, right there. If I had another O, it would both start point and end point will be pointing to one direction, one point, which is corresponds to OGO. Now, can I ask you one thing? If I have the start at the end of this algorithm, if I ask how many times does a pattern appear, can you quickly compute that using start point and end point? Because it's a range. End point minus start point plus 1 would give you the number of occurrences, isn't it? So how many times did I see a GO? Well, it starts at 2 and ends at 3. So 3 minus 2 plus 1. Okay? That's 2 times. If I had searched for OGO, Start point would be 5, end point would be 5. So what's the number of occurrences? Start point minus, end point minus start point plus 1. So 5 minus 5 plus 1 is 1 time. Let's do one more example. Let's assume that we saw, let's search for LOGO. I know that doesn't exist, right? LOGO doesn't exist in this string. So right now, if I were thinking about this algorithm, my start point, end point, if I had OGO, it would be pointing at 5. So what do you think will happen when you do this? You would end up getting a scenario where your end point will become less than your start point. The moment end point becomes less than the start point, you know that you have not found any occurrence. You can pretty much stop while you're recovering. Okay, so rather you essentially say while you're recovering, when you find that the end point becomes less than a start point, you can stop your algorithm saying that I haven't found it. Okay, does that make sense? Okay, all right, so that's it. Actually, sooner than I hoped, I essentially have shown how do you construct the Burrows-Willis transform and how do you do pattern matching with that. So this is basically how the algorithm works. The point is that if you do a suffix efficient, so how long does it take to compute a Burrows-Willis transform is a function of the algorithm you use to construct it. From 2004's version, I think you could write it in n log squared n, but after next week's topic, you will be able to construct BWT in on time. Okay. Now, I must say that week 4 will perhaps be the most challenging part of this unit. I must warn you. But again, so this is an example of a very simple. In terms of idea, it might still be complicated. Be perfectly fine to accept that this is tricky to crystallize the understanding, but I promise you that all you have to do is just persist, and this will basically say, that makes sense, and it's beautiful. This is one of the algorithms that is beautiful, that is reachable. Okay. Next algorithm is basically giving you a peek of how complex thinking is, how beautiful algorithms are designed, but the beauty is by working through some detail. The detail is fairly subtle, is what we would basically be exploring. At any stage, we are there to help you. So don't think that I'm just going to talk about an algorithm. We are all passionate about your learning. So if there's any part that you don't understand, we are there to help you. Yeah. So don't feel that you're left alone in this journey, and that I just want you to learn this without support. But for that, I want you to revise. And this is, please take this seriously. Coming into the next lecture, please revise what a suffix tree is and understand what it is trying to capture. What is the structure? So it's a tree structure of suffixes, isn't it? And you have to intimately understand what a suffix tree is before you understand why Yukonen had these tricks, these set of tricks that allow you to compute the suffix tree very efficiently. Yeah. So with that thing, I think most of you are falling asleep. Long lecture, but I hope it was worth it. Thank you. Any questions at all? No worries. See you soon. I'll have my Zoom consultation tomorrow at 9 a.m. So make sure you come in if anything's troubling you. Yeah. Do you know how to fix fix that. I actually sent an email to the people and they have not yet responded. So I'll try my best again, yeah? Fair enough. Yep.
I just want to ask how to construct this table, by the way.
You don't have to construct the table. The whole idea is that you just need this row, this column, and you get, all you're doing is, it's essentially a function of, it's all a function of that column and 2 pointers associated with it.
Yeah, I mean, so for now it's checking the pattern now. I mean, just from the start, like, should we actually create this table or
No,
not?
it's all, so all you're doing is, you're just going to go narrow down. So let's assume that, go to the very last slide. Okay, maybe I can, just 1 second, I'll be with you. So if you just look at that last slide, it takes a while. What happened? Okay, so what you have is a start point, end point, and these pointers, right? The pointers are pointing to position 2 and 3. Yeah?
Yes.
So pointers are pointing to position 2 and 3. If you look at suffix array 4 and 1, suffix array 4, 1, 2, 3, 4, there's a GO, and 1, there's a GO. All you need is the last. You essentially driving the whole thing with these 2 pointers. All this is for your understanding of how the correctness of how the algorithm works. But you never have to construct that. Think about that. Yes.
So I have a question regarding the complexity of more and more.
Very nice. So it's a very good question. We'll just step out, and because it's a longer question, I'll give a talk. So is there any question that I can quickly answer?
It's something like the assignment, but it's like really quick. So for the question, the second question, the wildcard is given in the input, right? At a set.
Yeah, the dot would be a part of your input.
Yes.
Yeah.
Okay, cool.
So you don't have to worry about, you know exactly where it is if it exists.
Okay.
So potentially it might not be there,
Yeah.
but if it's there, you'll only see one instance of it, and it's a problem defining variable. So
Yeah.
you get an input, you know exactly where it is.
Exactly. Cool. Thank you.
Okay. Right. So let's step out and we'll work out the details,
Okay.
because I think I'll leave the room for the next lecturer. Okay. Oh, I'll be. You can carry on. I'll come. Yep. Yeah.